Do I get extra credit for saying that every time?
Yeah. Here, take a mental note. Do y'all have any questions on the homework? I know we haven't finished, quite finished 10-1, but any issues you run into? Okay, so we were looking at this example here. We're talking about a series now. 10-1 is just an overview of both sequences and series. So we looked at this series, and it says find the first four terms of the first four partial sums. And we listed out the terms here, a sub 1 through a sub 4, partial sums here on the right. And we said that it diverged because, I mean, maybe we were looking at the partial sums and saying, well, the sum continues to grow. But if we look at the fact that the sums continue to grow and compare that to the terms themselves, maybe this is 0.444, etc. Maybe we can gain some insight as to, one of the things we consider in a later section, and that's the fact that these terms, 1, 2, 3, 4, a sub 1, 2, 3, 4 rather, they're getting larger. So like this, the a sub 4 term is larger than the a sub 3 term, and the a sub 3 term is larger than the a sub 2 term. And that's directly related to what we see with the partial sums getting larger and larger, right? So like if a sum is going to get larger and larger, each term has to be bigger than the previous term. So we'll just make a note of that. Each term is larger than the previous term. I mean, if we're going to say it mathematically, we would say that a sub n plus 1 is larger than a sub n. Yeah.
Did you run into the opposite of that, where it still diverges, just going the other way, every term gets smaller?
Every term gets smaller, yeah. So like we kind of alluded to that yesterday. Just because every term gets smaller doesn't necessarily mean that a series will converge. We said it was necessary for the terms to get smaller in order for a series to converge, but it wasn't sufficient enough to guarantee convergence. And again, the classic example of that is the 1 over n or the 1 over k series. Although the terms get smaller, that series diverges. And we'll see. We'll have an explicit test in 10.4 that'll tell us, 10.5, 10.5. We'll see explicitly how to test that actually does diverge. But for now, it's good to keep that in your head as like the classic counterexample too. Also, note that the limit, I forget we use k, yeah, the limit as k approaches infinity, we're kind of just tying all this together with various observations on our terms, 2k over k plus 7 times the square root of k. What would that limit equal? Infinity over infinity, so you could do L'Hopital's rule, but the leading term up top over the leading term on bottom tells us that limit's going to be 2. Yeah, so this is kind of like if we looked at the terms themselves without even adding them up, if we just looked at it like as a sequence or just a list of numbers, when k is 1, we get a fourth. When k is 2, we get a third. But these terms here, the a sub n's, when we look at the limit as k approaches infinity, that's what we're looking at. We're just looking at the terms, right? We're not, the summation is not involved in that limit at all. So that might, you know, it goes hand in hand with what we've noticed. The sum just continues to get larger because as k approaches infinity, in other words, as that index gets larger and larger, the kth term, whether that's the millionth term or the 10 billionth term, is getting closer and closer to 2, right? That's what that tells us, that term, the terms towards the tail end of that, if there is such a thing, are getting closer to 2. And then we think about it in terms of, well, I'm summing all of those things up. So eventually, if I could go out far enough, it would be 2 plus 2 plus 2 plus 2 plus 2, right, forever. So the thing we're just going to note here is that the limit of the terms is not 0. And so the limit of the terms not being 0, that is enough to guarantee something diverges. Because again, what it says is that each term is subsequently larger than the other. Or if you look at it in terms of the limit of those terms, in other words, the terms themselves don't get smaller and smaller. They're approaching 2, so it's 2 plus 2 plus 2 at the very end. So this is enough for divergence. And I just want to, you know, it's not crucial that we remember this at this point, but it certainly will be when we get about midway through chapter 10. Oh, we should say it diverges. Okay, so just a couple of things to note there. Does anyone have any questions on that? Okay. So another type of series that we'll see in 10.3, similar to this one here, 1 over the sum from 1 to infinity of 1 over 3 to the k. Just find the first 4 terms of the sequence of partial sums, and then make a conjecture or a guess about the value of the series. So really the first thing we need to do to get the sequence of partial sums is we actually need to know what the terms of that series are. So the first term, a sub 1, would be what? 1/3. 1/3. The second term, 1/9, because it's 1 over 3 squared. And the third term, 1 over 27. And the fourth term, 1 over 3 to the 4th. So we're just indexing k and how it specifies, starting from 1, going to 4. We're stopping at 4 because we just need the 4th partial sum. So when we look at the first partial sum, it's just the first term. The second partial sum would be 1/3 plus 1/9. Which will, this is 4/9. The third partial sum is 1/3 plus 1/9 plus 1/27, and it's 13 over 27. And fourth partial sum, 1/3 plus 1/9 plus 1/27 plus 1 over 81. And that's 40 over 81. So maybe it'd make more sense if we're just asked to look at the partial sums to say, does that converge or diverge? You could look at it numerically, like we have 0.3333 here, we have 0.44444 here, and so forth. But if you're looking for like an explicit formula for that partial sum, it's more beneficial to leave them as they are. That way we can see like a numerical connection, like what's the formula for the numerator and what's the formula for the denominator. So really that's all we were asked to do. We're going to do a little bit more, but what we're looking at is the sequence of partial sums here. And based off of that, we want to determine, will that series converge or will it diverge? So I mean it's sort of limited. There's only 4, so I mean we might have a harder time guessing with just 4 terms, but what do y'all think? Will that converge based on what we're looking at? Because remember, we're not looking at, these aren't our terms anymore. These actually represent our sums. So our terms were simply 1/3, 1/9, 1/27, 1/81. And we certainly see that, okay, those terms are getting smaller and smaller as we progress. But does that mean if I add all of these terms up that are getting smaller and smaller, does it mean that they're going to converge? So we just look at their sums instead. 13/27, 40/81. So I mean, it's certainly, and if you have to put that in your calculator, it's fine. But it certainly appears that based on what we're computing here with the 4th partial sum, is that it would converge. Those sums aren't getting drastically larger. I mean, and even if they were, doesn't really mean, or doesn't really guarantee us anything. But the idea then was to take this further is, just like when we looked at that example of 1/2 to the k, can we actually come up with an explicit formula for our nth partial sum? So we have 4 things to go off to try to build that pattern. So that's what we're going to try to do. Can we find an explicit formula for our nth partial sum? Maybe we should scoot this down. Okay, so I think the denominator is pretty straightforward because it's always just a power of 3. So how can we come up with the numerator? And I don't know at this point that it's intuitive. And 10.3 will actually justify what we're about to show. But for now, I think it's probably a little bit harder to guess like what that pattern is, or to come up with what that pattern is. So we'll just kind of write a few of these down just so we can get a sense of the general pattern they take. So let's say we'll write a series out here. I guess we could break this up. Let's say the nth partial sum numerator and we'll look at the nth partial sum's denominator. And the formula for the nth partial sum. here. It's not straight at all. Okay. We are dealing with a very specific type of series here that we'll talk about in length in 10.3. But we're specifically talking about the series that are like from 1 to infinity, or from 0 to infinity, of r to the n. So in the above example, our r is 1/3. All right, so for example, if we had the sum of 1 over 12 to the k, the denominators for these, like we said, are always going to be really straightforward. So the denominator for the series 1 over 12 to the k is just the power of 12 to the k. But the numerator would be 12 to the power of k, that quantity minus 1, all over 11. And if we go back to that example where we wrote our explicit formula for the nth partial sum for 1 over 2 to the k, you can kind of get a sense of how these things fit together. So the nth partial sum formula explicitly for 1 over 12 to the k would be 12 to the k minus 1 all over 11 times 12 to the k. Remember the one we had for 1 over 2 to the k? We wrote that out as the nth partial sum was 2 to the k minus 1 over 1 times 2 to the k. So how about the sum from 1 to infinity on 1 over 31 to the k? What would the formula for the explicit formula for the nth partial term sum look like? We can write out the numerator, or the denominator again would just be 31 to the k. The numerator is 31 to the k minus 1 all over 30. So the formula for the nth partial sum is 31 to the k minus 1 all over 30 times 31 to the k. And so for us, the sum from k equals 1 to infinity of 1 over 3 to the k, what would the nth partial sum for that look like? What's the formula for the nth partial sum? Sorry, I wasn't mindful. We're talking about the nth partial sum, so just to be clear, this needs to be n, not k. So for the sum 1 over 3 to the k, what would the nth partial sum be? yeah. 3 to the n minus 1 all over 2 times 3 to the n. A denominator, of course, as we saw, were powers of 3, but the numerator is a little less straightforward. You might have, you would have eventually gotten there, but it's just a lot of trial and error. I think it's easier just to spell it out now. And then in 10.3 show why that is the way it is. Okay, so that's the explicit formula for this nth partial sum here. Okay. So then, what is having the nth partial sum do for us? An explicit formula for the nth partial sum. What does that allow us to do? Write a limit as n approaches infinity, because as we saw, let's go back, as we saw here in this definition, the thing that we've starred here, the limit of a series, but they're just using a sub k. Ours a sub k is of course 1 over 3 to the k, but the limit of a series, or sorry, the sum of an infinite series is the limit as n goes to infinity, which is the limit as n goes to infinity on the nth partial sum. So once we have the formula for the nth partial sum, to say that the limit on the nth partial sum is actually just the sum of the series itself. So then we need to compute the limit as n approaches infinity on this thing here, 3 to the n minus 1 over 2 times 3 to the n. So what would that limit be? 1/2. Yeah, again, leading term on top is 3 to the n. Leading term on bottom is 2 times 3 to the n. So we can look at it here. Remember, the general approach to computing limits at infinity was to take the highest power in the denominator and divide everything by that. So it's 3 to the n on the bottom, so we'll divide everything by 3 to the n. So that gives us 1 minus 1 over 3 to the n, all over 2. We'll just say here as n approaches infinity. So 1 over 3 to the n as n goes to infinity just goes to 0. So you have 1 minus 0 over 2, or 1/2. But I think it's a lot more efficient to get accustomed to the leading term over leading term situation.
If you had like 3 to the n and then get another like 3 to the n minus 1, would you just ignore that as well?
Where at? Like in this?
Because you said you take the highest power, so if you have like
Oh, I see. Yeah.
2 different powers, you just still just stick with the leading, the highest power.
Yeah. Yeah, even something like that, the limit at infinity would still be 1/2, because we're still only looking at these two things. So the sum that we're dealing with is actually 1/2. I mean, it converges to 1/2. And so that's, a more technical and official way to think about those things. Right now, we're just, hey, look at the partial sums, does it converge? But all of this stuff that we're doing as like an extra to what the problem's asking is things we're building up to, or are things we're building up to, so. Anyone have any questions on this? Okay. So the last series, the sine of 18n plus 1 pi over 2. Does the series converge? If so, what is the sum? So what are we going to do here to answer that question?
Say 4 or 5 terms.
Yeah, we'll just look at the first 4 or 5 terms without adding them up. We're just going to see what happens when the first term, a sub 0, when n equals 0, rather, because it's our first term. So we figure out what's the sine of 0 plus 1 pi all over 2.
So just 5 over 2.
Yeah, sine of pi over 2 gives us 1. Our second term, when n is 1, would give us what? Sine of 19 pi over 2. Which would be, it's going to be 1 or negative 1, but which one is it? Negative 1? What do y'all think? Negative 1? All right, so not looking great so far. I mean, maybe it does because our sum is just 0, but third term, when n is equal to 2, sine of 37 pi over 2 equals 1. So are we going to ever get anything but, it's always going to be the sine of some pi over 2, right? So it's always going to be 1 or negative 1. I mean, maybe we need to look at more, I don't know, but you can if you want. Next term is negative 1. And so that pattern continues, 1, negative 1, 1, negative 1. Remember, again, these are just the terms. So what would we say here? It's going to diverge, right? So the first partial sum, if we wanted to look at it, would be 1. The second partial sum is 0. The third partial sum is 1. The fourth partial sum is 0. And since those partial sums don't approach one specific number, the sums are actually alternating between 1 and 0. Does that make sense? The sums, the sequence of partial sums. But the terms themselves kind of allude to that. So either we could look at the terms or the sequence of partial sums. Doesn't necessarily matter. So either way, the series diverges. Any questions on this example? All right, well, that'll finish 10-1.
As far as an exam, how much work would you want us to show? Are you gonna like ask us, hey, show me 4 terms, or?
Actually, I honestly, by the time we get to the exam, there's so much content in this section, or this chapter, I won't ask you to write out sums and partial sums. So I didn't realize until yesterday that the blank notes that I posted didn't have these definitions. So if you printed those off and you don't have that, I'm really sorry. The blank notes had them. I don't know what happened when I converted them to a PDF. But I've re-uploaded the blank notes with these definitions, and they're here for our notes if you're printing those off.
Is that 10-1?
This is 10-2. Yeah, so in 10-2 is all about sequences. And some terminology for sequences that you'll be asked. In your homework, it's going to ask about certain terms here. And so we're just going to get familiar with what it means. Increasing and decreasing, I think we're all sort of aware of what that means. In terms of a sequence, though, increasing means that the next term is larger than the previous, a sub 1 is larger than a sub n, and decreasing when the next term is smaller than the previous. But then they introduce these terms non-decreasing and non-increasing. So those are probably somewhat new, but non-decreasing means that the next term is larger than or equal to a sub n. So what does that actually mean, like in words? What does that mean?
The next term is the same as
The next term is the same as the
the
previous or larger than, right? So when we say it's non-decreasing, we mean, another way to think about that is to think about the sequence as increasing or constant. So it could be increasing and then constant for a while, then increases again, then constant for a while. It just means that it never decreases. Okay, same thing with non-increasing. Means the sequence never starts to increase. So non-increasing, similar thing. It means that it's decreasing or constant. So non-increasing, non-decreasing are a little bit more utilized in like certain theorems, particularly when we look at this term that's monotonic. So if you've got a monotonic a monotonic sequence, then it's non-increasing or non-decreasing. And what they say there is that just implies that it moves in one direction. Like we're always steady and moving up, or we're steady and then moving down. Whatever we're dealing with, if it does that, it is monotonic. So either non-increasing or non-decreasing implies it's monotonic, and a bounded sequence just means that it has an upper bound. So this capital M, such that in magnitude, the terms are less than or equal to that particular number, whatever it is. At least one theorem that we look at, there's a bunch of other ones that we don't talk about. One theorem that we look at for sure deals with the fact that if we have a sequence that's monotonic and bounded, then we can say something about that sequence. Okay, so that's just some terminology. Y'all have any questions on that? Okay. So these are some visual examples. The homework write this out. 10.2 homework will ask if a given sequence is monotonic and bounded. So for this, again, I'm not going to test you over graphing a sequence because it's just time consuming to plot all these discrete points. So here just use the, just graph them. I posted a link in the announcements for a sequence plotter for you to use. And it'll take you to this page right here. This function is going to be different. It's defined in x in terms of x. So if your sequence is 1 over n, then you would just type 1 over x here. Because what they're gonna do is they're gonna give you a sequence like n over n plus 1, and then they'll say, is that sequence monotonic? Is that sequence bounded? Does it converge? So instead of just like plugging numbers in and looking at all of the different terms, just graph those. So we'll plot that as x over x plus 1 in this plotter here. And then you can just move the slider to see all the subsequent terms. And then from the image itself, should be pretty obvious what it does. So is that sequence that we're looking at there, the n over n plus 1, is that monotonic? Yeah, is this sequence non-increasing or non-decreasing?
Yes.
Non-decreasing. It appears that it's always increasing. But what is it like when we say that it's bounded? Really, what does that mean if the sequence is bounded? Yeah, it's approaching a single term. It doesn't necessarily mean that it has to approach a single term if we just say it's bounded. But the combination that this sequence is monotonic and bounded. Monotonic tells us that it never changes direction, and bounded means that there's some number that it's all of those terms are less than. And from our plot, we plotted even more points. We could clearly see that it looked like there was a horizontal asymptote sort of in the continuous realm. So this thing here converges. Switched it up on me. Okay. Here's the example from figure 817. Here's an example of a sequence that is monotonic. It doesn't change directions. It's non-decreasing, but it diverges. It's not bounded. So we see here that it diverges, and they're saying it diverges monotonically. So just, again, we should be familiar with those terms, particularly for 8.2's homework. Here's one that alternates. We have the negative 1 to the n up top. So remember that just changes the sign over n squared plus 1. So here you see those things, they're larger, but as we progress through more terms, they still oscillate, but those oscillations are getting smaller and smaller. So what would we say about this? Is it monotonic? No, it changes direction, right? It's like this sawtooth. So this thing's not monotonic. Does it converge? Yeah. You know, we might say it converges via oscillations. I don't know if we need to get that descriptive about it. So we're seeing like an example, we had a monotonic bounded series sequence. Sorry, I'll try to be mindful. I spend so much time talking about series. We had a monotonic bounded sequence that converged. Second example, we had a monotonic unbounded sequence that didn't converge. Here we have a sequence that's not monotonic, but it converges. In 8.5, what's going on there? Is that monotonic? Does it converge? No. We have a divergent series here. And notice that one's defined as a recursive relationship. We do have oscillations here though, so you know, it diverges via oscillations. We could be a little more descriptive if we wanted to. And then the last figure here, what's going on there? Is it monotonic? No, you have to look at the order at which this unfolds, right? Our first term is here, our second term is here, third term, fourth term, fifth term. All right, so it's changing signs, it's alternating. What would we say, that converges or diverges? Diverges, why?
Because it doesn't go towards any one particular number.
Right, exactly. We're not approaching one specific number. Now, if this graph that we're looking at here in figure 8.4, if that were just all of these, the even terms, if it were just those by themselves, then we would say that it converges. Or if it were just the odd terms, it converges. But we have it alternates between positive and negative. So it's very similar to that last example in 10.1 that we looked at with the sign of whatever, 18n plus 1 pi over 2. It's the same kind of idea there. So for those on your homework, just graph them. I'm not going to have you graph anything on the test, so you won't be missing out any like important skills by doing that. Geometric sequence. It has the property that each term is attained by multiplying the previous term by a fixed constant called the ratio r, and they have the form r to the n, where the ratio r is some real number. So here again, we would see, graph the sequence, 0.4 to the n. Does it converge or does it diverge? Before we graph it, what's our r in this example? 0.4. So let's see what this does. So we'll just graph 0.4 to the x. So it seems to converge, right, to 0. And does that pretty quickly. I mean, pretty quickly for the computer. To do like, to even compute 10 terms, I think would kind of be a pain if we're doing that by hand. Maybe not so much with this one, but. So clearly, hopefully, we see that it converges to 0. Does it converge monotonically? Yeah, it's a non-increasing function. Okay, so the ratio there was 0.4. It converges. What do you think about negative 0.4 to the n? Non-monotonically? Yeah, so we see the negative. Does that mean every term is negative?
It need to be outside.
Yes, yeah, exactly. Note the parentheses, right? The negative is inside the parentheses, also being raised to the nth power. So we could view this as, oops, another way to view this to where it's maybe a little more explicit is to rewrite this as -1 times 0.4. All of that's to the n, and then we can write that as -1 to the n times 0.4 to the n. So we see that 0.4, we've already looked at that. The only difference here with the -1 to the n being in front of that is that these terms above in example 1 just alternate in sign. So what's our ratio here for this one, example 2? If we just looked at it as the geometric is defined, it's just r to the n, right? We don't have that alternating switch out front. So we have to view the ratio as the -0.4. So we see there's our second term, first term's down there, second term, third term, fourth, fifth, sixth, seventh, so forth. Just a little above, a little below. I'll just put a few more in here. Okay, so there's our graph. Let's make a note at what we said here. R is -0.4. -4/10. This thing converges. I guess we'll say this here via oscillations. Any questions on that? What about 1.4 to the n? Yeah, it's not gonna be bounded. So you can just think of the exponential function 1.4 to the x. These are just discrete analogs of our continuous functions. Let's see if it'll do this here. So there's our exponential function 1.4 to the x. And there's our sequence 1.4 to the n. So is that monotonic? Yes. We've got a monotonic sequence rather, but it diverges. It's monotonic, but it's not bounded. Sequence diverges. And then so what's going to happen with negative 1.4 to the n? Do what? Okay, so let's check that out. Negative 1.4 to the n. So say third. And so you see it's, we'll zoom in a little bit. Happens pretty quickly that the terms just keep getting larger and larger. It's not monotonic, and it diverges. Here we have oscillations again because of the negative 1 to the n. But with these four examples, we're going to move into like the definition or the theorem that says, given any geometric sequence, what does that ratio have to be in order for this series or sequence to converge? So just it's on the next page. Just keep in mind here that we looked at both a positive r and a negative r here, saw that both of those two converged, both a positive and negative r here, and saw that those two diverged rather. Okay. The one thing we did notice, we might be compelled to investigate it further. I mean, this is probably how things happen in the real world. If you're establishing all of these rules, you're messing around with all this stuff, and you say, well, hey, every time I have a monotonic sequence that's bounded, it seems to converge. And then so you would set out to try to prove that. So here it is as a theorem. Any monotonic bounded sequence converges. So another example of something like that would be the inverse tangent of n. Again, if you can think of what the inverse tangent of x looks like as a continuous function, this is going to look like that, but it's just the discrete version. So instead of trying to draw it poorly by hand, I'll just go ahead and plot it here. Maybe this will capture it, maybe it won't. We can change these values perhaps. I wonder why. Okay, it's actually be all of these. So let me put this in here then. we're only talking about our ends being positive. But we know that this is arctangent right here. Do y'all remember where the horizontal asymptotes were? And yeah, negative pi over 2. Could we maybe we'll leave that in there as well. No, take it out. But there's the inverse tangent. Again, just these discrete elements, not everything in between. So it's just another example of a sequence that's bounded and monotonic, converging to pi over 2. It's really not like, it's a super short theorem, but it's really not a trivial thing to prove at all. So thank goodness we don't have to do that. That was like the worst math class you'll ever take if you ever take it. It's called real analysis. It's so bad. Be aware. Okay, we do have limit laws for sequences because, you know, as we stated in 10.1, if we're given a particular sequence and we want to know what does it converge to, and that just entails us computing the limit at infinity, because all we're dealing with are the terms anyways. What do the terms approach? Limits at infinity. So here are limit laws for various situations dealing with sequences. And it says, assume that we have two sequences, lowercase a and b, and they have limits, capital A and capital B respectively. If we take two sequences that converge to A and B, when we add them up or subtract them, it converges to the sum A plus B or the difference A minus B. So in other words, what we're seeing here, not explicitly shown, is just based on our limit laws. If I have the limit of a sum or a difference, then I can just take the sum or the difference of the limits. Same thing when we have a constant multiple on a sequence that converges. It just converges to the constant times A, where A is what it converges to. In other words, it's C times the limit of A sub n. So the limit of a product is the product of the limits. So, you know, at this point, they probably look more like limit laws than they do laws involving sequences. And then the limit of a quotient is the quotient of the limits. Provided the b is not 0, of course. So limits at infinity you may or may not remember very well. If you don't, you've got to reacquaint yourself with those, because it's in a lot of things that we do in chapter 10. And with limits at infinity becomes, you know, the leading term over the leading term type analysis, L'Hopital's rule. And then we'll look at another property here that allows us to, sometimes we can even bypass L'Hopital's rule. But you have to be familiar with these. So a few of them here, and we'll look at a few more. But the limit as n approaches infinity on 2 plus n, or sorry, 2n plus 1 over n would be what? Infinity? Plus 0, right. Well, the 1 over n goes to 0, right? Because you have 1 over a number that's getting larger and larger. The quotient gets smaller and smaller. So you know, I don't know, we'll just write it out symbolically here. So that term, second term, approaches 0. 2 times n, of course, approaches infinity. And so if that were our sequence, 2n plus 1 over n, we could say that it diverges because the limit on that sequence, in other words, the terms get larger and larger is what that's saying. Okay, how about n plus 1 over n cubed? 0? Does everybody agree? We've got an n squared up top and an n cubed on bottom. Leading term over leading term. You don't have to write all of this out. I'm just kind of justifying. And then number 7, there's not a lot we can do with that as far as like actually calculating it because we don't have a specific sequence. But this is just to remind you that if we have roots, and we could even make this more general, if we said that this is some sequence to the power of a over b, or maybe we have the fourth root of that sequence squared, or to the third, or whatever. What we can do is pass this limit into the root. So we can take the bth root of the limit at infinity on f of n to the a. So we can pass those things through. Sometimes it's helpful. We'll write this one out too. All right, do y'all have any questions? So a lot of this stuff is really just based on properties of limits at infinity that we've looked at maybe in Calc 1, I think. And the properties of limits themselves. So then L'Hopital's rule is also something that shows up. Again, you need to be familiar with specifically the ones that apply to L'Hopital's and the ones that indirectly apply to L'Hopital's, which were these indeterminate forms on page 8. Infinity minus infinity. 0 times infinity. Those 3 there. Because honestly, any one of those situations could come up in some given sequence, just like it could come up in a particular function. So, got to be familiar with those.
Wait, what?
We'll go back to that. So that's page 8. Okay, so find the limit of the sequence natural log of 1 over n, or determine that the limit does not exist. So again, if this is just a sequence, then we're saying, well, I'm computing the limit at infinity on the terms themselves. So the limit at infinity is going to show me what the terms do as I progress. So we're going to calculate this. And before you apply L'Hopital's, just make sure that it's of the form 0 over 0 or infinity over infinity. Otherwise, if you apply L'Hopital's rule, it's not going to work. It may work. You might get lucky, but yeah. So what would this be? Yeah, because we have the natural log of 1 over n. 1 over n itself is approaching a really small number, 0. But we've got the natural log of something that's getting closer to 0. The natural log gets closer to negative infinity. So this is, we'll just say here by direct substitution, that's negative infinity over infinity. And that is a form that directly applies to L'Hopital's. So all we'll do is take the derivative of the numerator and the derivative of the denominator. We're just going to indicate that we've used L'Hopital's rule. Limit. What's the derivative of 1 over the natural log of n? Well, if it were just the natural log of n, we would just say the derivative is 1 over n, right? But the argument isn't n, it's 1 over n.
You can just take the negative out.
We could take the negative, we could take the reciprocal, we could change the reciprocal of 1 over n, yeah, but since we didn't, let's work with this. Well, so it's 1 over n times the derivative of 1 over n. Remember chain rule? So times the derivative of 1 over n. Or it's 1 over n to the negative 1. Or sorry, if we looked at it as n to the negative 1, it's 1 over n to the negative 1 times the derivative of that, right? Sorry, I missed that. It's 1 over the argument. So I should have wrote 1 over n. So what is 1 over n times negative 1 over n squared? Negative 1 over n, yeah. So that's just equivalent to the limit as, remember L'Hopital's rule, and then simplify before you try to evaluate the limit again. So we simplify it as negative 1 over n, we can calculate that limit as 0. So that if that were our sequence, we would say the sequence does converge to 0. The terms approach 0 as n gets larger. Okay, do you have any questions on that? So we'll take a break. We're going to skip example 9 because we have a more difficult or more general example in example 10. And then once we see example 10, we can go back and answer example 9 really easy. But moving forward, this example here in number 10 that we're going to show what that limit is, I would commit this to memory because it is a fairly constant sequence and it is a fairly consistent limit. So it's almost like we're going to prove this formula so that you can keep using it without justifying it. You just know that this is this. Okay. So we'll take a break before we do that. Okay, so here, what kind of situation are we dealing with here? Yeah, so what is the limit? What form does the limit take? So as n goes to infinity, what does a over n go to? 0. So in the parentheses, we have 1 plus 0. B times infinity is still infinity. So it has the form 1 to the infinity, which is indirectly a L'Hopital's rule, but we first have to express that 1 plus a over n to the bn power as a quotient. So the strategy for those types, 1 to the infinity, 0 to the 0, and 0 to the infinity to the 0, was to rewrite the expression. So we're going to rewrite 1 plus a over n to the bn as e to the natural log of 1 plus a over n to the power of bn. And so it's not immediate as to why this helps, but again, in the power itself, we have log raised of something raised to a power. So we're going to rewrite the power of e as bn times the natural log of 1 plus a over n. And so that's a little better. Now we have a product. Now we have this product on the power. Remember, when we compute the limit as whatever goes to infinity on e to that power, the limit as n goes to infinity, specifically here, doesn't affect e. All it does is affect the power. So when we compute the limit as n goes to infinity on our given sequence, we know that's equivalent to computing the limit as n goes to infinity on this thing. Which again is equivalent to just computing the limit on that power. And just leaving e where it's at. So does everyone remember that rule? It's just it just deals with the inverse properties of natural log and e. And so we'll take this limit and compute that, see what we end up with. But when we compute this limit directly, what kind of an expression do we end up with? Yeah. So you end up with infinity times 0, which we might have expected because we turned the power to another power, or the base to a power here, into a product using that property. So then the question is how do we take a indeterminate product like 0 times infinity and turn that into a quotient? Yeah, we involve the reciprocal. So all we do here again is just rewrite the limit as n approaches infinity, natural log of 1 plus a over n over 1 over bn. That algebraically is equivalent to our product, except that this limit, by direct substitution, gives us the natural log of 1 over something that's getting smaller and smaller. So it's kind of like those indeterminate powers, if you will, are sort of twice removed from L'Hopital's. You've got to first rewrite it, then it turns into an indeterminate product, and you rewrite the product as a quotient, then that's something you can directly apply L'Hopital's rule to. So it's this thing above that we're applying L'Hopital's rule to. So we take the derivative of the top. It's 1 over the argument times the derivative of the argument 1 plus a over n. So what's the derivative of 1 plus a over n with respect to n? Negative a over n squared, right? All of that over the derivative of 1 over b times n, which is what? Negative 1 over b times n squared. And before we evaluate this limit, we'll simplify. So algebraically equivalent to the limit as n goes to infinity. See what we have on top. We have our negative a over n squared plus an. All over. Well, let's do this. Do this one step at here. Then we'll invert and multiply the negative 1 over bn squared. So we simplify the top, multiply by the reciprocal in the bottom. And we've got the limit as n goes to infinity. We've got a negative abn squared over negative n squared minus an. Distribute the negative 1 in the bottom. Yeah, you can cancel the negatives. So then what is that limit? Can we compute that limit as something meaningful?
Yeah, should we cancel an n first?
You can. You can cancel the ones, you can cancel the n's. Either way, we're all going to be looking at a similar situation. Remember, this is the limit as n goes to infinity. What we have up top is a polynomial in n, and on bottom a polynomial of n. So leading term over leading term has us computing the limit as n approaches infinity. Which is negative ab, let's write it out, negative ab over negative 1, which is ab. So yeah, if you're canceling the negatives and a factor of n, you're still ending up with that limit being ab. So that's not the limit, right? That was just the limit on the power of e. Yeah, so then we've got to take this back up where we were and say that this is equal to e to the ab power. And that's what that limit is that we originally started with. E to the AB. Did everyone have time to get this here? And to leave it there for a minute? So then the limit as n approaches infinity of 1 plus a over n to the bn is equal to a to the b, e to the ab power. For example, what's the limit as n approaches infinity for the sequence 1 plus 5 over n to the 4n? E to the 20, e to the 5 times 4. So I would just remember that pattern. As you see, it's a lot of work to justify it, but we'll just move forward accepting that as fact. It's easier to remember the formula, I think, and hopefully the process is somewhat reminiscent of something you've done before, but still, it's time consuming.
If we remember that formula, will we ever need to show how to get there?
No, unless I explicitly ask you to like prove this, we can accept this as fact. And if it does show up on a test, I'll give you notice. So then, with this in mind, we go back to example 9. What does example 9 equal? E to the
You did with 1.
yeah. Because A is 1 and B is 1. So 10 was just the more general case for that. So I would definitely remember that. Does anyone have any questions on number 10? So, okay, the procedure here that we just went through is there if you need to reference that. But each one of these indeterminate forms, 1 to the infinity, 0 to the 0, and infinity to the 0, they take the following forms, which we see that they're actually, when we rewrite them, they're indeterminate products in disguise. So the 1 to the infinity, for instance, takes the form of infinity times ln1, which is 0 times infinity. We see actually all of them are 0 times infinity. All right, find the limit of 1 over n to the 1 over n. Or 1 over n to the 1 over n, which is 1 over the nth root of n. So I don't know that it necessarily matters which form you work with, but we're going to just look at it at the limit as n goes to infinity on what we had originally, 1 over n to the 1 over n. Just so it's in a form that we can directly relate it to. So as n goes to infinity, we've got 0 to the 0. Now, in a lot of instances, like arithmetically speaking, 0 to the 0 is 1. 0 over 0 has to be 1 in order for the, remember how you expanded a binomial with the binomial theorem? Maybe, maybe not. But there was a theorem that said, hey, to expand this a plus b to the, x w power, it's going to take this particular form. 0 over 0 has to be 1, but in those instances, we're not talking about a limit. Here we're talking about the base getting smaller and smaller as the power gets smaller and smaller. So just because we write these 0 over 0 things doesn't mean it's literally 0 over 0, right? In the sense of a limit, it just says it's approaching 0 to the 0th power. So again, the first step here is to rewrite one over n to the 1 over n as e to the 1 over n times the natural log of 1 over n. And then compute the limit on the power. So let's rewrite that n on the bottom. Like that. Do we know that limit? Yeah. Isn't that what we computed in example 8? The limit was 0. That's e to the 0, which is 1. So that's the limit as n approaches infinity of 1 over n to the 1 over n, or 1 over the nth root of n, 1 over the 5th root of 5, 1 over the 10th root of 10, et cetera, et cetera. All right, so that's L'Hopital's rule. How it shows up could be any one of those forms. The other technique for computing limits at infinity, especially on trig functions like sine and cosine, where, you know, a part of that or a portion of your quotient or your function or your sequence doesn't exist, is to use the squeeze theorem. So if we just look at it as the limit as n approaches infinity on the sine of 6n over 5n, then we're going to have, what's the limit as n goes to infinity on the sine of 6n? Yeah, it doesn't hone in on a particular value. It doesn't grow arbitrarily large either. All we know is it's in between 1 and -1. So any number in between 1 and -1 including is what that limit is. So since it's not infinity, it doesn't approach 0, we say it doesn't exist. So those limits on like sine and cosine, they don't exist. And we have something that doesn't exist, but we know is in between 1 and -1. So it's like some finite number. And the denominator here is getting larger and larger. So we have to like make sense out of that. What is that limit? Is it going to be 0? Is it going to be 1? What happens here is that we have to squeeze or sandwich this not well-behaved function or sequence, sine 6n over 5n, in between two things that are well behaved. So just as something a little bit more straightforward, if somebody said that they're thinking of some number that's less than or equal to 10 and larger than or equal to 10, what number does that have to be? It has to be 10. 10's the only number that fits that criteria. So if you understand that, you understand the squeeze theorem. Except for the squeeze theorem is applied in terms of limits as opposed to, a numerical statement. It does end up being a numerical statement, but so the idea is to say, all right, well, what do I know about just the sign of 6n over n? The sign of anything is where? In between 1 and negative 1. Give me some space here. Okay, so I know sign is in between those two values. And then so maybe that's not always the starting point, but the goal is to have this unknown in the middle, and what we're dealing with as our unknown is sine of 6n over 5n. So then we want to divide everything by 5 over n. Do we have to worry about dividing by 0 here? No, why not? Yeah, because n's approaching infinity in some super large number, not 0. So we're just dividing by 5 over n so we can get the middle piece to look like the thing we're actually dealing with. And then so we have this sequence in between two well-behaved sequences. And then so to answer the limit question, then all we need to do is compute the limit as n goes to infinity, because the limit at infinity on this thing is less than or equal to the limit at infinity on this thing, which is less than or equal to the limit at infinity on this thing. So when you're dealing with sequences, particularly whether they converge or diverge, and you're computing the limit at infinity and you see sines and cosines, it's generally a good practice to default to this theorem, because limits at infinity for sine and cosine won't exist. You've got to sandwich them in between or squeeze them in between something you know information about. So what's the limit as n goes to infinity on negative 1 over 5n? 0. And this is still this thing. And similar instance for the right-hand limit. It's also 0. So what do we know about the limit as sine 6n over 5n as n goes to infinity? It has to be 0. I'll run out of room, so I'll go up here and say this limit is 0. So let's just look at it in a continuous case, and then you can sort of omit most of the line and just fill in the dots. Okay, so we have, and maybe when you look at the continuous piece of it,
and you just look at all these discrete points. But you get the sense that those oscillations are getting smaller and smaller. So then we bind it by negative 1 over 5x and 1 over 5x. And so we know, like out here, since both of these functions approach 0 and sine is in between those two things, this sine function has to approach 0. I don't know what I got. I got some of it.
Of course, we would have just a bunch of dots instead of all of those things being filled in, but you get the idea. Do y'all have any questions on that? Okay. So the other thing that's super helpful that you may or may not have talked about in Calc 1 was the idea of growth rates, comparing certain functions to other functions and saying, or in classifying them, saying that this function grows faster than this function and this function grows faster than both of those. That's the idea here. This double less than, or if we look at it as n to the p power is doubly greater than the natural log. It just means it's much larger than instead of just larger than. And the term much larger than, or the other way, much less than, it's arbitrary, right? It's like when we look at a limit, it says, well, for things that are sufficiently close, these things are arbitrarily close to that. It's a nebulous kind of term. For us, what it means is that this function here, n to the p power, grows much more rapidly than any power of the natural logarithm. And any exponential function grows much more rapidly than any of the functions to the left. So what we have from left to right are very slow growing functions. To the very far left, which are very rapid growth. And so, I don't know, you probably look at that and say, well, why is that helpful? Like, how could that possibly help us? Knowing which functions grow faster than other functions. So just then, let's consider the limit at infinity, as n goes to infinity, of some function of n over another function of n. So a couple of things here. Let's ask the question then. What is this limit? If let's start off with f of n. What is the limit if f of n grows more rapidly than g of n? Or faster? I mean, maybe we could say, I don't know if that's makes more sense. I don't know. Faster? Infinity? Was that a guess?
For an answer.
Yeah, I was looking for an answer.
Oh, okay, yeah. Infinity.
But, okay. So yeah, does infinity make sense? If the top function or the top sequence grows faster than the bottom, the numerator is getting larger much quicker than the bottom. What, same question. What's the limit if g of n grows faster? Zero. Yeah. The bottom's getting larger much more quickly. The quotient gets smaller and smaller. What's the only other outcome here?
They grow the same.
They grow at the same rate. If they grow at the same rate, then we've seen that before, that's like n squared plus 1 over n squared. The limit is just the coefficients there. Or 3 to the n over 2 times 3 to the n. They grow at comparable rates when you have a finite non-zero limit. But these primarily are what we're looking for, because we already know how to handle the comparable growth rates with L'Hopital's rule, any of that kind of thing. So particularly, let's go back to something we already looked at. Oh yeah. So for example, when we ask what's the limit as n approaches infinity of the natural log of 1 over n, if we know our growth rates, then you say, well, I know n grows much more rapidly than the natural log of something does, right? So here's the second situation. The function on bottom is growing much more rapidly than the function on top. So we know that limit is 0. We don't have to use L'Hopital's rule to answer that. And even better for us, you see these weird functions classified in the growth rate, particularly the n factorial and the n to the n. So I don't... Yeah, so the derivative, if you had to compute the derivative of n factorial, I don't know that you could do that. So for instance, the limit as n approaches infinity of n to the n over n factorial, we would say, well, that's infinity to the infinity, isn't it? Yeah, it is. But then L'Hopital's rule, how do we take the derivative? I don't know. But I know that n to the n grows much more rapidly than n factorial. So this limit will be infinity. So I think they're worth knowing because it can certainly save you a whole lot of time. And even if on the exam, if that's all you write, and you write because of growth rates, I think that's an acceptable answer. But don't just write the answer, because then I'll say, how do you know? Right? They just say, I know it's infinity because of growth rates. Or just say growth rates. I don't care. Just tell me you know what you're doing or what you're using. There is a continuous, not a non-continuous function in terms of the xy plane that does describe the factorial. It extends the factorial to fractional values. So we can do like what's 1/2 factorial. You can say what's negative 5/3 factorial. So there is a function that does actually extend the factorial to real numbers. It's not continuous at some places, but again, that's not something you even want to like deal with. The function is defined in terms of an integral, so it's not a friendly function. So this is super helpful. Okay, so for instance, if we're given some sequences here, A through G, classify these or order these based on their growth rate from the slowest growing to the fastest growing. So what's the slowest growing function or sequence? A through G.
C.
C, it involves the natural log. C sub n is the slowest. Okay. So we got that one. What next? B, where it's just n to a power. That's n to the p. So that's b sub n is the next slowest. Then what? D with the exponential. Then
G.
G, the factorial. And then finally a sub n is the fastest. Okay. So I personally think those are worth knowing. I won't test you directly and say, classify these functions on an exam, which one grows fastest. The way this is helpful is when you're computing limits. So we've seen many instances already where it's helpful. We don't have to use L'Hopital's rule. So if you want to remember these and reference them on the exam on how you're computing limits, I'm okay with that. I know maybe you didn't see that in Calc 1, but you're seeing it now, so I think it's worth committing to memory. All right, and that's kind of the limit techniques there for explicitly defined sequences. We can look at recursively defined sequences. And so, for instance, if we had the a sub n plus 1 is half a sub n plus 2, initial value is 5. It says make a conjecture about the limit or determine if the limit does not exist. So the trick here with these is you basically have to start off with an assumption, and we're just going to assume the limit as n approaches infinity on a sub n is something. Call it L, W, T, A, whatever. And if we're assuming this, let's ask the question, then what do we know about the limit at infinity for a sub n plus 1? Do we know anything?
It's bigger.
Yeah, it's the next term, right? It's the nth plus 1 term, but our assumption is that the nth term approaches L. So just think about it, maybe like if whatever series or sequence we're looking at, let's just say this is L. If I know like way out here that this term is approaching L, then what do I know about the next one? It also has to approach L, right? So remember, this n is totally arbitrary. We're just saying basically like the infinite term has to is approaching this limit, so the infinite term plus 1 also has to approach that limit, right? Okay, so that's our assumption allows us to then say, well, that term and for that matter, any subsequent term a sub n plus 1, plus 2, plus 3, all of those terms approach infinity. So that limit is also L, or whatever you called it. And so in the sense of n approaching infinity, then we take our recursive relation and say that that has to be L equals to 1/2 times L plus 2. So this is what we'll say. We'll say that, we'll just write it here. So as n goes to infinity, our recursive relationship is L equals 1/2 L plus 2. So if this thing does have a limit, remember that was our assumption. We just assumed it had a limit. If it does have a limit, then we can solve for L. So we have minus 1/2 L over here, which means L is equal to 4. So yeah, that seems reasonable here with this recursive relationship that it would approach 4. We start with 5, we take half of 5 and then add 2. Whatever that is, we take half of that and then add 2 again. So if this thing does have a limit, it would be 4. Make a conjecture about the limit. So that's our conjecture about the limit, that it's equal to 4.
So if it was infinity, like if it diverged,
Yeah.
what would the term show as? Like, so if it was a n plus 1 equals a of n plus 2, like that would grow indefinitely? So would,
Yeah,
would
so
we
'cause
get,
you-
like an unsolvable problem?
Yeah, you would have to take a different approach, because then if something like that, if I heard it correctly, you would end up with a false statement.
Yeah.
0 equals 2. 0 equals to 2. Okay, so I mean, it's, you know, maybe not a totally obvious technique. I think once you see it, then it's when it works, it's very useful. It's very clever. So these continued fractions, have y'all seen those before? There's certain numbers like pi and e, the golden ratio. Some of those numbers can be defined as continued fractions. I don't know that their utility is widespread, but it is an interesting way to think about a number. So they take this form here, 1 plus 1 over 1 plus 1 over 1 plus 1 over, et cetera, et cetera. But if we look at that in terms of a recursive relationship, we're taking 1 plus 1 over the previous number. So that's our recursive relationship here. The next term is 1 plus 1 over the previous term. The first term is 1. It says evaluate the first 5 terms of the sequence, where a sub 0 is 1. Then a sub 1 would be what? Yeah. So our n is 1 here, so a sub n plus 1 is 1 plus 1 over the previous, which is 1. So 1 plus a half. Is this 3 halves? Huh? What? Oh yeah, 1 plus 1. Yeah, my bad. It's too late. That's right. That was wrong. Okay. Third term. 1 plus 1 over the previous term. Yeah, did it. Third term, a sub 2, a sub 3. Fourth term is 1 plus 1 over the previous. 1 plus 1 over 3/2. 1 plus 2/3, 5/3. And then our fifth term, which is a sub 4, 1 plus 1 over the previous, 5/3. So we have 3/5, 8/5. So first 5 terms. And then assuming the limit exists, determine the limit exactly. We do the same trick. Assume that the limit exists. Means that we're assuming that the limit as n approaches infinity on a sub n is equal to something. Determine the limit exactly. So as n approaches infinity, our recursive relationship can be defined as L equals to 1 plus 1 over L. So I don't know, just it's maybe worth pointing out at this point, if you look at the terms of that sequence, we have 1, 2, and then we have 3 over 2, 5 over 3, 8 over 5. Do those numbers look familiar? The numerators and denominators individually? Huh? Yeah. So those, remember our Fibonacci numbers, 1, 1, 2, 3, 5, 8, 13? Okay. Solving for L, multiply through by L, we have L squared equals to L plus 1, or L squared minus L minus 1 is equal to 0, which is quadratic. So we use the quadratic formula to solve for L. What would you factor? Yeah, you can't, if you factor an L out, you'll have L, whatever, something, you'll have that equal to 1, and there's infinitely many choices for that. So quadratic formula, ULA, tells us that L is equal to the opposite of the coefficient here, opposite of B, plus or minus the square root of B squared minus 4 times A times C, all over 2A.
Is this C -1?
Yeah, -1. All over 2A. Okay, so we have 1 plus or minus square root of 5 all over 2. Yeah. What's our L?
It's a positive.
It's the positive of that, right? Because our sequence is of positive numbers. Say our sequence contains, I guess, positive terms. this is our limit. Any questions on that? So if you look at the Fibonacci numbers, 1, 1, 3, 5, 8, et cetera, and divide higher and higher of those, like 55 over 34, those successive ratios will get closer and closer to this number right here. It's just like 1.61828, blah, blah, blah. And so there's another way, as a continued fraction, we can define this golden mean. And that's really just a term from ancient Greece. They thought it was divine. They thought there was like, I don't know, it was kind of interesting,
Sounds
but
like God.
yeah, it was handed down by God, or whatever they attribute to that.
Somehow you could create gold
From a what?
They believe somehow you could create gold from it.
Yeah, it was related to alchemy too, right? Yeah. Okay, this is very similar. I think we'll stop there. Maybe you can give that a try. We'll mention that when we come back on Tuesday, and then start 10.3. So 10.3 and on, we start looking at series.